Okay. So at the beginning, I would like to raise two fundamental theorems of calculus. So the first one, okay. So let's let g of x be a real valued integrable function on across interval AB, and let g of x defined to be for all x from A to B. Okay. Then g of x is differentiable. Okay, at x equal to t for some t in AB. Then maybe I stated it the other way. Then if g of x is continuous, okay, at x equal to t, and t is in between A and B. Oh, AB. Then okay, so double then, I think that's not necessary. So I just say, then g of x is differentiable at x equal to t, and g of from t is equal to g of t. Okay, so that is the first fundamental theorem of calculus. Okay. So first of all, if we know g of x is a real valued integrable function on this closed interval. Okay, so that we can define indefinite integral, right, called capital G of x, by using the g of x as integrand. Okay, and x is also in between A and B. Okay. Oh, I think I can. That's the reason why I want to. I insert. Then g of x is continuous on AB. Okay, of course. So that we know that. So this indefinite integral is continuous on AB. Okay, so that is standard. The important thing is the second thing is that if the integrand g of x is continuous at a certain point t is in this closed interval, right? So if then this indefinite integral capital G of x is differentiable at the same point, and the derivative of capital G at t is equal to little g of t. Okay, so this is the first fundamental theorem of calculus. Okay, now let's see some consequence of the first fundamental theorem of calculus to our absolutely continuous random variable. Okay, so consider an absolutely continuous random variable x with a PDF f of x. Okay, so for that, we know that the cumulative distribution function, the CDF f of x of x okay, and by the definition that x is absolute continuous is to say that the PDF, this non-negative valued function, because as we say, PDF should be non-negative, f of x that is integrable. Okay, so that's why we can integrate over this interval to get the cumulative distribution function CDF. Okay, so it's f of x is this one. Okay, in particular, if we define g of x to be f of x minus f of say 0. Okay, so well, okay, for any t in such that t such that f of x at which f is continuous. Okay, so suppose we know the PDF is continuous at certain point t. Okay, we select an A, B, such that A is less than T, less than B. Okay, and define g of x to be f of x minus f of A, which is from A to x f of t dt. Oh, sorry. Sorry. For all x in the interval. Okay. Okay, so we defined a function, and so this function is just the difference of these two. Okay. Okay, so by the first fundamental theorem, of calculus, okay, G is differentiable at Gx is differential at x equal to t, and the G prime t is equal to f of t. But we know the G of x is f of x minus a constant. But G prime t is equal to f prime t. Okay? Or since G of x is equal to f of x minus f of A, f of x is differentiable okay, at x equal to t, and f prime t is equal to g prime t is equal to f of t. Okay. So this is implies. So the first fundamental theorem of calculus says that for an absolutely continuous random variable, its CDF, okay, is differentiable at every point where such a PDF is continuous. Okay. And the derivative of the CDF is equal to the value of the PDF at t at the point t. So that, okay. Any questions? Okay. So this is the consequence that we know a random variable is absolutely continuous. So if means that we find a PDF for such a random variable, right? So once we find a PDF, okay, and then we know that the corresponding CDF is differentiable at every point where the PDF is continuous. Okay, so we know the consequence. And then the other question is, how do we know okay, so how do we know that a continuous random variable is absolutely continuous? Okay, as we know, if a random variable is absolutely continuous, then x is continuous, as we discussed before, which can also be seen from here, because g of x is continuous. Okay, g of x is continuous, so f of x is continuous, of course, at every point. Okay, right. So if a random variable is absolutely continuous, then it is continuous. Right. So continuity is a necessary condition for absolute continuity. But conversely, if we are given a continuous random value, means that we are given a random variable whose CDF is continuous. How do we know that it's absolutely continuous? How do we know that? Okay, and part of the answer, right? Part of the answer is by the second fundamental theorem of calculus. Okay. All right. So now we state the second fundamental theorem of calculus. Okay. The statement is here. If a real valued function g of x is differentiable, okay, on across the interval, by the way, because we are considering closed interval, so how do we define differentiability at the endpoint? Okay, we mean for the left endpoint, we mean right derivative exists at A. Okay, you know the definition of right derivative and left derivative, right? You know that, right? So I don't want to write it again. Okay, so now, I ask you to know, when I say differentiable on a closed interval, then at the two endpoint, we mean one-sided derivative exists, or one-sided differentiability. Okay, so that is our understanding. Okay, mutual understanding for that. Okay. Okay, so I just ignore the statement here. All right, so that say, so g of x should be differentiable at every point on this closed interval, including the two endpoints. Okay, every point. Okay, it's important. Okay, this is the condition. And then, its derivative g prime of x All right. So this derivative is integrable on AB. Okay. It is possible that a function is differentiable, but its derivative is not integrable. It is possible to find such a pathological function. Okay, even though it's very strange, but there exists such a strange function. Okay, which is differentiable everywhere on the closed interval, but you can't integrate this derivative at all. Okay, right? So it's integrable. Integrability can be assured when the derivative is continuous, right? Continuity always implies integrability. Okay, so if this real value function is continuously differentiable, all right, on the closed interval, then that would be enough. That's sufficient. But here the condition is a little bit more general. That we just require the derivative is integrable. Means that it allows discontinuity at some countable many points. Okay, so anyway, but so that then is that then when we integrate, because it's integrable, right? Then when we integrate the derivative over this closed interval from A to B, then we get a result. This result is GB minus GA. Okay. So we can recover back. Or you can get another way. This is equal to GX minus GA for all. You can say this is more informative, right? You can return back to your original function g of x within a constant either, like minus GA. Okay? You have minus GA here. I think that is clear, because if you add a constant to your original function, then the sum have the same derivative as the original one, right? That's why when you integrate over, you have a constant to be free. Okay, so you have a degree of freedom. Okay, so that is so the second fundamental theorem of calculus says that you integrate derivative. The first fundamental theorem, you differentiate an integral. Okay, say right? Because calculus, you have two kind of operation calculus: differentiation, integration, right? So you can do the integration first and then do the differentiation. Or you can do the differentiation and then do the integration later, right? And what is the connection between these two operations in calculus? All right, the answer is from these two fundamental theorems. Okay? So you have to remember both fundamental theorem as the connection between differentiation and integration. Okay? But don't forget the conditions, right? That you know the conditions, okay, of the statement here before you can apply both theorems. Okay, so that is the second fundamental theorems of calculus. Okay, now, and we need a property okay, a property of a monotone increasing okay, functions which differentiable on the whole real line. Okay. Oh, maybe because I want to maybe I stated not only one property of a monotone increasing function f of x, which is differentiable right? Maybe I'll try put it more general first. F prime exists and is finite f of x has a finite and the non-negative derivative f prime of x at almost every x in the real line. Okay, so when you look at a monotone increasing function, okay, then this monotone increasing function has a finite and a non-negative derivative at almost every point x in the real line. maybe I'll say on the interval. Okay. So it may not have any derivative at this point. Okay, but this point, wherever it's scattering, that the total length is 0. Okay. Okay, so the meaning. So let me say what we call at almost every point. So let X to be the set such that f of X does not have any f is not differentiable at X. Okay, so suppose we define X to be the set of all points such that f is not differentiable. Then the length the total length of X is 0. Okay, so the total length of X is 0. Okay, so that means that f of f is not differentiable, and so except some point, all right, and whose length is 0, then this monotone increasing function has a finite and non-negative derivative. Non-negative derivative because it's in monotone increasing. Okay, so that you have non-negative derivative. Okay. And the second thing is that if we assign arbitrary value to f prime X at X where f is not differentiable. Okay, if f is not differentiable at some point, then of course f prime X does not define, right? So this one is not defined at all, right? And so we can assign arbitrary value to, right, because we want to create a function, a derivative. Okay, so we can assign arbitrary value to f prime of X at X where f is not differentiable. Okay, then f prime of X is integrable. Okay, on AB. Oh, okay. Oh, by the way, another thing. And is bounded on the real line. Okay, so then f prime of x is integrable over the real line. Sorry, I forgot to put this condition. Boundedness is very important. Okay, so so we have this one. So that is two properties of monotone increasing function. Okay. So the first statement says that for any monotone increasing function, maybe I will write down it's a domain. For any monotone increasing function f of x, it has a finite and a non-negative derivative at almost every point. Okay. All right. So this is a very interesting result. This is only particularly true for monotone increasing function, not for every function. Okay. And the second thing is that if we assign arbitrary value to each point such that f is not differentiable, okay, so that f prime of x is a function on the real line. Okay, it's a for example, you can assign 0 values for every x. For f of prime of x, such that f is not differentiable at x, you can apply 0 value of that. And if f is bounded, then the derivative is integrable. Okay, over this one. Okay, so now we will answer our question here. How do we know that a contingent random variable is absolutely continuous? Okay, so we will state that theorem by a theorem we call 5.1.b. Okay, if the CDF f of x of a random variable x is differentiable, okay, on R or on the real line, then f of x is equal to f prime of x, f prime of t, sorry. Okay, then this CDF can be recovered from its derivative. Okay, from its derivative. And the derivative f defined to be f prime of f is a PDF of x so that X is absolutely continuous. Okay. All right. So this theorem gives a partial answer to our question, not a full answer, because this just gives us a sufficient condition, not a sufficient necessary condition. Okay. Okay. So it requires that this CDF must be differentiable. As we know, differentiability implies continuity, right? So if the CDF of a random variable is differentiable on on the real line, then it is continuous. Okay, then it's continuous. So of course, so this random value is a continuous random variable. Okay. But important thing is that we can recover it here. So when we compare the theorem with the second fundamental theorem of calculus, we know that the statement of the second fundamental theorem of calculus require that not only g of x is differentiable on this closed interval, but its derivative is integrable. All right. So the missing part here is that I didn't say that the derivative is integrable, right? Explicitly, but from the two properties here, that the CDF is a monotone increasing function, of course. Okay, and in here we say that it is differentiable every point. All right, so we don't need to assign arbitrary value to its derivative, right? Because it's already there. Okay. All right, and so that and f is bounded. Why? Because a CDF has value between 0 and 1. Right? Its value is between 0 and 1. So it's bounded. And so that the second probably say that the derivative is integrable. Okay? Alright, so even though I didn't state that the derivative of the CDF is integrable, but it is implicitly implied from the above properties here as a bounded monotone increasing function. Okay. All right. So and also here we have this result, right? When we integrate over the derivative, we get the original function back here. Okay, so we get back, but this one is minus infinity, and f of minus infinity is 0. So that this one, as a goes to minus infinity, this goes to 0. So disappeared, and so you get the f of x here. Okay. So as a goes to infinity, so when you take the limit, this definite integral becomes to improper integral, right? And this f of a goes to 0 because f minus infinity is 0. Okay, and so you recover this one. So this is basically, the first part is basically the second fundamental theorem of calculus. If you work with the second property of monotone increasing function. Okay. Okay, and from this one, if we call the derivative as f, and this f should be non-negative. Why? Because that by the first property, f has finite and non-negative derivative. Okay, so every derivative is non-negative. Okay, so this f is a non-negative function, and it's a non-negative function, and you get this one. And as we know, this is actually probability that the x is less than or equal to x. Okay. So from that, you can go back to see that for every interval. Okay. So this implies. So from here, this implies that, for example, okay. Okay, so you get this one. So for an interval, you get the integration here, and so that the derivative f little f is a PDF. Okay, and so x is absolutely continuous. Okay, any questions? Okay. All right, so we go to discuss expectation and variance. Of random variables. We first recall that a real valued function on the sample space is a random variable if for any interval I of the real line this is subset okay, it's an event of interest. I.e. in the sigma h by f. Okay. Okay, and so it seems that by definition you need to test all types of interval I to see if this subset is an event of interest. Okay, you can loosen your burden a little bit by the following theorem. So a real valued function x on the sample space x is a random variable if and only if for all a in the real line x greater than little a is an event. Okay, so you need to test just this type of subset to see if it's an event of interest. Okay. All right, and the proof is quite straightforward. All right, x less than equal to a. All right, this is actually okay. You see, there are quite a few okay, for such subset. Okay, and that is the complement of this event. Okay. All right, so we only need to show this function because the forward function is trivial. Right. All right, so suppose that we know these types of subset of the sample space is an event of interest for all little a on the real line. Now we see that if our interval is this type, right, and this is just the complement of that. So this is also in F. Okay, and how about x in A and infinity? So that is x is greater than equal to A. Okay. And what is that? Well, that is the intersection of x greater than a minus 1 over n. Okay. Because as n become bigger and bigger, a minus 1 over n will approach to a from the left-hand side. Okay. And so that because we are concerning this, okay, and so this is a. Here is a minus 1. Here is a minus 1/2, etc. Okay, and so as n go up, this event they are event of interest. These events going to smaller and smaller, right? Okay, so they become smaller and smaller because they're shrinking, right? They are shrinking to here, pushing there. So the event becomes smaller and smaller, and when we take the intersection, this intersection is exactly equal to this subset, and so we have countable intersection of events here, right? So it's also in F2. Okay, so these two types are also events. Now how about x in A infinity? This one. So this is x greater than no, sorry. that would be minus this one. Okay, so x is xa. All right, and well, we can take this as x less than equal to a minus 1 over n, and from 1 to infinity. Okay. So it's here. This one is a, so we are going to here. Now this is a minus 1, a minus 1/2, etc. Okay, and so oh, no. Sorry. A. And here, a minus 1, a minus 1/2. Okay. All right, so these events become bigger and bigger. Okay, this go this way. So this is become bigger and bigger. Okay. All right, and so when we take the union will become to this one, because it will never reach to the point A. And this is in F2. Okay. So you have these three types of event already in the sigma algebra here. Now, how about x is in the open interval? So that is this one. But this is equal to x is greater than a intersect x less than b. Okay? So this is the intersect of these two events, and we have proof x greater than a and less than b here. So the intersection is also in F. Okay. Similarly, we have other two cross. So that is x greater than a intersect x less than equal to b. But x less than equal to b here is also in F. So this is in F2. X is in oh, okay. So this is x is greater than equal to a intersect x less than b. And so this type here and this one, they are in F, so the intersection is also in F. And the last one, okay, is also in F2. Okay. All right. So the reverse direction has been checked, and the forward direction it's trivial. Okay, or you can say it is from the definition of a random variable. Okay. All right. So the theorem. So this theorem gives us a less burden than what we needed to do by the request from the definition. Okay. Is that okay? Okay. So later on, we just need to verify a function, a real value function on the some space to be a random variable. We just need to verify that this particular kind of subset is an event of interest. Okay. Okay. So let's take a break of 5 minutes to 2:30. Yes. Okay, so we continue our discussion here. Now, we recall a real valued function, okay, g of x of a random variable x can be regarded as a data processing of the observed random data. Okay, so we draw a diagram before. Okay, so if we perform a random experiment, we have an outcome called omega, and then we have a measurement device. Okay, give us under the name of the measurement device called X. So we have a real value. Okay, suppose the result of the measurement. Okay, when the outcome is omega, you get a numerical value called x of omega, and then you go a data processing unit called G. Okay, so you get G of x. Okay, omega there. For example, you take the absolute value, right, of the measurement value, or you take the square of the measurement result. There are a lot of things you can do, all right? Or you can take the exponential of this measurement result. Okay, yeah, called data processing. Okay, so a question is, how do we know that G of x? So G of x, what is G of x? G of x is from sample space to R. Okay, it's a random variable too. So how do we know? Okay, so remember x goes to R, and this is x, this is G, so this will be G circle x. Okay, so it's a composition. So G of x is a composition. Sometimes we call it this one a composition of two functions. Okay, the x function from the sample space to the set of all real number, and G is a real value function on the set of all real number, for example, and so the composite becomes to a real value function from the sample space to R. So once again, we have a question that how do we know that the g of x is a random variable too, because it's a function defined on the sample space. Okay, and we will see the answer. All right, the answer is on the intrinsic property of the data processing function. G. Okay. Okay. All right. So let U be a subset of the real line the inverse mapping of a subset U under G is defined as G minus U such that the function value is in U. Okay. So the inverse mapping of G is okay. So basically, inverse mapping it's okay. So it's from the power set of R to the power set of R. Okay, so that is the every so the inverse mapping. So the inverse mapping in here, we don't care whether G is 1-to-1 or onto, right? Because we are not going to discuss the inverse point-wise inverse mapping. Okay. Okay. So that and so so this is G. And suppose, for example, U is this interval, and so the inverse mapping go back here, maybe okay. So they go to okay. So this is U is here. Okay, so every subset of the real line goes to a subset of the real line. Okay, so U is a subset of R, go to another subset of R. Okay, and this is what is the subset in here? Well, we include all the x such that the function value is in U. Okay, so this is called the inverse mapping. Okay. All right. So now the key to answer the above question is that can we make sure that for any interval I of the real line all right, so this one, so this subset by our definition is a subset of the sample space such that g of x is in I. Okay, so that the data processed result is in this interval I. Okay. And so this is going to say that such that x of omega, this one is in I, means that the x of before data processing, the value here is in the inverse mapping of I. Okay? And this is equal to x is in g of inverse of I. Okay. So the key is here. When we want to ask if this subset is an event of interest, okay, we are asking the same thing, that by using the random variable x itself to ask for that this subset is an event of interest. Okay, so these two are the same subset of sample space X. Okay, but this one is expressed directly by the original random variable X. Okay, so we are asking for that for any interval I. This one, okay, this one is an event of interest. I.e., a member in the sigma algebra. Okay? Okay, so can we make sure this thing that for every interval I, this one is an event of interest. All right, and by the aid of the above of theorem 5.2.8 here. Okay, we can only the I, the interval can be more special. We need only to check whether g of x greater than little a, okay, which is x is in g inverse of a, okay, to infinity, okay. So this interval, this particular interval, is an event of interest. Okay? All right, so for every, so this is the A to, so this is the, all right, so it's a ray, open ray, from A to infinity. Okay, and G inverse of this subset. Okay, and X in this should be an event. All right, so consider, and so this property, as I mentioned, the key is on the intrinsic property of the data processing function G. So consider G to, so now we consider a real valued continuous function. G on R. Okay, so now we see. So if the data processing function G is continuous, okay, this is quite often to occur in practical situations. Okay, then for an open interval I, finite or infinite. Okay, so this is an infinite open interval, but you may have finite interval too. So for any open interval I, the inverse mapping G inverse I of I under G is a disjoint. Is a disjoint union of countably many open intervals, say J1, J2, maybe finite or infinite. Okay. So let me draw a picture. G of x. So G of x is continuous function. And suppose we trigger This is a finite open interval. Okay. What is the inverse G inverse I? Well, so when you draw, you can draw okay, and so that you have okay, so that you have this open interval, oh. Oh, yellow color. Okay. All right, so this is J1, J2, J3, J4, J5, J6. So you can see that G inverse I is J1, disjoint union J2, disjoint union J3, disjoint union J4, disjoint union J5, and the disjoint union of J6. So there are 6 open intervals. Right? So for every open interval I, maybe this one is a finite open interval, but if you can have an infinite open interval like this one. Right? The inverse mapping will become to a disjoint union, okay? Disjoint union of countably many open intervals. Yeah. Okay, so it's a property of continuous functions on R. Okay, and okay. I will explain why we have this result. First point, if I is an open set, okay, then the inverse mapping, because G is continuous, so the inverse mapping is an open set too. The first concept. Now, if we have open set on the real line, all right, so the inverse mapping open set on the real line, then the open set becomes to disjoint union of connected open set. Connected open set on the real line should be an interval. That is the basic for you to have the intermediate intermediate value theorem in calculus because of connectivity. All right, and so, and how many connected how many open interval do you have? Because every open interval has at least one rational numbers. So that pieces, that disjoint open interval, at most countable many. Okay, so that's why we have countable many open intervals, and they are disjoint. Okay, because they can decompose into connected open component. Okay, so that is the property of real line. Real line, the only connected open set is open interval. Okay, that is the, so it's a topological property of the real line. Okay, it's a topological property. Okay, but the illustration is just can be seen from this example. Okay, this example. Okay, so you can regard this as a factor. Okay, as a factor, and so now g of x in the open interval, as we know, is equal to g is in the inverse mapping of I, but x is in the disjoint union of I, j, I. Okay? And this is actually, okay. It doesn't matter to have disjoint union or just union, that's fine. But, well, I just want to put disjoint union to emphasize the truth, here, the fact here. Okay, so, and you can see that this is in F2. Of course. Why? Because Ji is open interval and X is a random variable. So by definition, this is an event of interest. And you have a countable union, right? Countable union here. So that it must be also in the sigma algebra. Okay, so that's okay. So we settle our problem. If the data processing function g of x is continuous, then g of x, this new function, becomes to a random variable too. Okay, so it's also a random variable. Okay. Right, but sometimes, continuous function is not general enough. So sometimes we will consider real value function. So a real value function on R is called piecewise continuous if they are countably many points AI with AI less than AI plus 1, such that Gx is continuous is continuous on this open interval for all I. Okay. Okay. So we can consider piecewise continuous function. Now there are many piecewise continuous function. Okay. So you may have this one. Okay, so this is a piecewise continuous function. For example, here you can think about here. This is A1, A2, A3, A4. Okay. So in here, I just draw a piecewise continuous function which has 4 points of discontinuity. Okay, it's A1, A2, A3, and A4 here. Okay, can you see? So it's piecewise continuous because in each piece, okay, that g of x is continuous. Like here. So this is piecewise continuous function. And at the point of discontinuity, the function value can be arbitrarily defined. For like this one or here, right? It can be arbitrary. All right. So now, then for an open interval I, find out our infinite. The inverse mapping G inverse I of I under G is a disjoint union of countably many open intervals J1, J2, in the union I of AI plus 1. Okay. And possibly some of the singleton AI okay. So let's see. We may take like here. I take this one. Open here. Okay. So okay. So this is our I here. And the inverse mapping. Sorry, I should. This is open circle. I'm sorry. Here. Oh, I should use red color here. Okay. Okay. So you see, we have this one, and including the point here. So I have a point. And here we have open interval. We have open interval. And here we have open interval, but including the point. Because the point is here, inside here. And we have open interval, and open interval. Okay, so we have J1, J2, J3, J4, J5, J6, J7. All right, and then I will write down the G inverse of I is equal to the shown union Ji, I from 1 to 7. Union, the point A1 is inside union. The point A2, okay, but not A3, not A4, right? Okay, so you can see the situation. Okay, so now we have g of x in the open interval, which is x in g inverse of I, which is equal to x is in ui, ji, disjoint union, k of sum a, aik, okay, and this is equal to disjoint union of I in ji and disjoint union of k, x equal to a, ik. Okay, and of course this is in F, because that AI, this is equivalent to the two endpoints are the same. Okay, So they are a kind of, this is a special types of interval, cross interval, okay? And okay, so as x is a random variable, this is the event of interest. And because j sub I, each j sub I is an open interval, so this is an event of interest. And the union are countable, countable unions, so it's in F2. All right, so from the above discussion, so a partial answer to the above question. So the question is that how do we know g of x is a random variable too? Is the following theorem. We use that theorem 5.2.b. If x is a random variable and g is a piecewise continuous real valued function on R, then g of x is also a random variable. Okay. Okay. All right, and so piecewise continuous real valued function will be broad enough for our applications. Okay. if we encounter a more specific function which is not piecewise continuous, then we will look at C and C again, right? But that would be some special cases. But for most of cases we encounter in practice that we can have this result. Okay, so we settle this question. Okay, we have to settle that. Okay. And so for the rest of this semester, now I will feel confident if I raise some signal processing functions. Okay, because we will deal with functions on random variables a lot. Okay, in the later chapters. Any questions? Okay. All right. So I think I have to stop here. All right. And I'll see you on Thursday.